In 2003, selected Iraqi aircraft at Taqaddum were deliberately buried to protect them from coalition air attack. This was one concealment measure, not the only option facing the entire Iraqi Air Force. For the aircraft in this story, burial traded immediate use for the chance that the hardware might survive. The target of this operational sacrifice was the Mikoyan-Gurevich MiG-25 designated by NATO as the Foxbat B. This was an advanced, supersonic asset measuring approximately 70 feet in length. Retaining these airframes meant ensuring they did not exist as targets when coalition forces advanced. At Taqaddum Airbase, located roughly 155 miles west of Baghdad, ground crews executed this directive. They moved the heavy aircraft out into the deep sand dunes surrounding the airfield. To properly conceal the asset, they had to dismantle it. A complete supersonic airframe presents a massive geometric profile, making subterranean concealment nearly impossible and ground transport across shifting dunes highly restrictive. When the aircraft was recovered, its swept wings were absent from the main fuselage. Public records do not establish when, how, or by whom they were removed. Their absence carried an immediate consequence. Wings contain fuel, hydraulic, electrical, and control connections, and without them, the recovered aircraft could not fly. Whatever the original reason for their removal, the machine was already an incomplete airframe. Recovery teams could not locate the wings, and their fate remains unconfirmed. That missing geometry would define every later stage of the aircraft's recovery and display. Months later, as United States forces secured Taqaddum, the intelligence-gathering operation shifted to locating these hidden assets. The broad, arid perimeter offered many possible burial sites, making a blind search difficult. Contemporary official accounts emphasized that concealed aircraft could remain undiscovered without precise knowledge of where to look, or until shifting sand exposed some visible trace. Public sources do not identify the exact information that led personnel to this particular MiG-25. The search team nevertheless reached the burial area near the airfield. The visual clue was stark and immediate. The twin tail fins were visible above the sand, marking the location of the buried aircraft. Public accounts do not establish whether wind, incomplete covering, settlement, excavation, or some later disturbance exposed them. United States forces were not recovering a complete, flight-ready aircraft, but a concealed airframe whose principal fuselage had survived underground. What condition is a massive supersonic aircraft in after months locked beneath shifting desert sand? A substantial but publicly undocumented depth of sand covered the aircraft, imposing uneven overburden across a fuselage more than 70 feet long. Most aerospace structures are engineered to be as lightweight as possible, prioritizing aerodynamic lift and fuel efficiency over blunt crush resistance. A buried airframe can experience uneven soil pressure, settlement, and localized loading it was never designed to carry. The danger was not a single dramatic pressure number, but an uncertain pattern of overburden acting across unsupported panels, openings, and structural members. The exact stresses cannot be calculated from the public record because the burial depth, sand density, compaction, support conditions, and deformation measurements were not published. Photographs from the excavation show covering material around the fuselage, including netting and tape-like material. Public records do not establish who applied it, whether the entire aircraft was wrapped, or which openings were sealed. The covering may have been intended to reduce the amount of sand entering exposed areas. That covering could reduce contamination, but it could not guarantee preservation. Sand entering intakes, equipment bays, seals, or mechanisms might abrade components and complicate later inspection, cleaning, and conservation. The airframe remained a heavy and awkward recovery load, but its actual weight during extraction is not documented in the public record. Material alone did not determine the outcome. The MiG-25 was unusual because its airframe made extensive use of welded, heat-resistant nickel steel, with smaller amounts of aluminum and titanium, rather than relying primarily on lightweight aluminum alloys. This heavy steel construction was not originally intended for subterranean storage. It was a direct engineering response to the aircraft's thermal design limits. At speeds approaching Mach 2.83, the airframe experiences intense aerodynamic heating produced by compressibility, shock waves, and viscous effects in the high-speed airflow. Traditional aerospace aluminum loses its structural integrity and softens at these extreme temperatures. While titanium offers high strength and heat resistance at a much lower weight, it was exceptionally difficult to machine and expensive to manufacture in mass quantities during the era of the aircraft's design. The Soviet engineering solution was to utilize heavy nickel steel alloys for the majority of the airframe construction, accepting a massive weight penalty in exchange for thermal survivability. This material choice produced a heavy, heat-resistant airframe built for sustained high-speed flight. It may have contributed to the fuselage remaining recoverable, but no public engineering assessment proves that steel construction alone supplied the crush strength that saved it. How, then, do engineering teams safely break a buried airframe free from compacted sand? Discovering an advanced high-altitude reconnaissance platform wrapped in low-tech camouflage netting and adhesive tape creates a sharp evidence contradiction. The target was identified as a Mikoyan-Gurevich MiG-25RB, a high-altitude reconnaissance bomber designed to operate in the lower stratosphere at extreme speed. Yet, the initial site assessment revealed this sophisticated aerospace asset swathed in crude ground-level materials. Covering material remained around parts of the fuselage, offering some protection from additional sand intrusion. It was not, however, the only factor governing internal contamination, and the aircraft's internal condition was not documented in the public account. Before the airframe could be removed, personnel excavated around the buried aircraft. Contemporary photographs confirm the excavation, but do not establish a strict hand-clearing sequence or the exact balance between manual work and heavy machinery. The detailed stabilization procedure, therefore, remains unconfirmed. The most critical hazard zones were the massive air intakes located on either side of the forward fuselage. The aircraft utilizes two turbojet engines housed deep within the rear fuselage. Each of these power plants requires an immense volume of airflow to generate 22,500 pounds of thrust. To feed that extreme thrust capacity, the aircraft features massive internal intake ducts. These large geometric voids are highly vulnerable. If the covering failed, additional sand could enter the intake ducts and complicate inspection of the engines. Sand inside the ducts could add weight, abrade surfaces, and complicate handling and inspection. Public sources do not quantify how much entered this aircraft or document a measured shift in its center of gravity. Recovery personnel had reason to limit further contamination, but the exact internal condition remains unconfirmed. The excavation also had to expose enough of the airframe for recovery personnel to judge where mechanical force could be applied. Public accounts do not identify the jacking points, trunnions, engine mounts, or inspection sequence used on this aircraft. The defensible conclusion is simply that the buried structure had to be uncovered and assessed before extraction. The manual clearing phase transformed a buried mystery into a documented, stabilized site. The intake voids were secured. The intelligence value of the internal engines was preserved from contamination, and the critical structural hardpoints were visually confirmed to be intact. The massive airframe was no longer completely entombed, but it remained firmly locked in the bottom of a deep trench. With the hardpoints exposed, the operation faces the hazard of applying brute mechanical force to an aerospace structure. Using blunt military earth-moving equipment, against a fragile 25-ton aerospace artifact creates an immediate trade-off edge. The manual clearing phase stabilized the site, but pulling the massive dead weight from a compacted trench requires heavy force. The primary recovery constraint shifts from environmental protection to extraction hazard management. Aircraft structures are specifically engineered to handle distributed aerodynamic loads across their broad surfaces during flight. They are absolutely not built to withstand concentrated mechanical pulling from a static, buried position. Applying raw horsepower without a controlled vector risks tearing the fuselage apart. The operation required heavy earth-moving and recovery machinery. Contemporary United States Air Force photographs confirm the use of heavy equipment around the buried aircraft, although the exact vehicles and division of tasks are not fully documented. In an active combat theater, this was a military engineering recovery rather than a conventional archaeological excavation. Any attempt to pull a buried airframe had to limit uncontrolled point loads and further structural damage. Public sources do not disclose the cable attachment points, load calculations, or rigging plan used on this MiG-25. The exact extraction geometry, therefore, remains unconfirmed. Heavy equipment removed sand and freed the airframe from the burial site. Photographs show the broad outline of the operation, but they do not confirm a graded extraction ramp, perfectly aligned tow vehicles, synchronized cable tension, or the aircraft rolling out on its own tires. Those details remain unconfirmed unless a primary recovery log can establish them. The principal fuselage was successfully removed from the sand. It remained incomplete, and public records do not state that it emerged without buckling, distortion, corrosion, or localized structural damage. With the excavation complete, transport became the next constraint. The aircraft's size imposed a dimensional problem during onward transport. Both vertical stabilizers were removed to facilitate the move, although the public record does not identify the transport aircraft or publish the exact clearance calculation. The incomplete aircraft still had to leave the combat theater, and its size complicated the move. Beyond the documented removal of the vertical stabilizers, however, the route, transport aircraft, cargo door geometry, ramp angle, loading sequence, and any requirement for a pressurized hold remain unconfirmed. The twin vertical stabilizers were large structures at the rear of the airframe. Recovery personnel removed them for transport, but no public account shows that the team debated a choice between destructive cutting and methodical unbolting. How the stabilizers were detached is not publicly documented. Any scenario involving abrasive saws or cutting torches remains speculation, and such work around an unassessed military aircraft could carry serious hazards. The verified fact is that both vertical stabilizers were detached for transport. The available sources do not identify the tools, fasteners, cranes, personnel positions, or lifting sequence used. The detailed unbolting operation, therefore, remains unconfirmed. The successful removal of the tail section permanently solved the transport geometry problem, allowing the stripped fuselage to slide cleanly into a heavy transport hold. This action also formalized the ultimate outcome of the field operation as a partial recovery. The fuselage, the twin internal engines, and the dismantled vertical stabilizers were completely secured for safe transit. Yet, the massive swept wings, detached and hidden by Iraqi ground crews prior to the initial burial, were never located or recovered. The primary airframe was successfully extracted from the sand, but it would permanently remain a fragmented machine. Where does an incomplete, sand-scoured supersonic bomber go once it leaves the combat theater? We can clearly verify the physical condition of the recovered main body today, but the massive swept wings remain completely lost to the original desert environment. In 2006, the secured airframe arrived at the National Museum of the United States Air Force. Transitioning this massive aerospace structure from an active military intelligence asset into a static, long-term public exhibit immediately forced a critical conservation trade-off. Most aerospace museum displays rely on a philosophy of complete visual restoration. If an aircraft arrives damaged or is missing external components, standard practice dictates that technicians will fabricate sheet metal or fiberglass replacements. The operational goal is typically to present the airframe exactly as it appeared on a pristine flight line. For this specific recovery, employing that standard restorative logic would permanently overwrite its historical truth. The curatorial team instituted a strict policy of artifact incompleteness. The decision to leave the aircraft incomplete forces the public to confront the reality of its extraction, rather than the illusion of its flight capability. The first physical requirement was reassembling the components that the combat engineering teams had successfully extracted and transported. The heavy vertical stabilizers, which were methodically unbolted in the field to bypass the strict transport dimensional limits of the cargo aircraft, were hoisted back into their factory positions. Technicians carefully realigned the massive steel structural fins and secured them directly to the original aft bulkheads. Securing the stabilizers required precise torque mapping to ensure the original threads, previously packed with desert sand, were not compromised during the reconstruction. However, the heavy structural wing roots flanking the central fuselage were left entirely bare. Exposing these massive mounting brackets and the disconnected hydraulic manifolds is a deliberate forensic decision. The absence of the wings serves as the primary physical proof of the pre-burial disassembly mandate. By refusing to fabricate false aerodynamic surfaces, the museum ensures the airframe accurately reflects its historical recovery condition. The missing geometry transforms the display. It is no longer just a high-speed reconnaissance platform. It is a permanent physical record of a ground-based concealment strategy, visually anchored by its missing parts. Beyond the missing structural components, the museum conservation staff faced a complex environmental stabilization problem. The heavy stainless steel fuselage had successfully resisted the immense static loads of the trench, but the burial environment had permanently altered its surface chemistry. Desert sand is highly abrasive and retains alkaline particulate that traps moisture. Even when placed inside a climate-controlled museum hangar, trapped sand deep within the internal structural seams acts as a catalyst for long-term galvanic corrosion. The technicians had to carefully arrest this active corrosion hazard without erasing the physical signature of the burial. Utilizing aggressive chemical stripping agents or abrasive media blasting would completely clean the heavy steel skin, but it would also destroy the forensic timeline of the artifact. Instead, the team executed a highly localized stabilization process. They systematically vacuumed the internal crevices and applied low-impact solvents exclusively to active oxidation points, ensuring the structural integrity of the metal remained stable. Managing the ambient humidity of the display hall became a primary defense mechanism, neutralizing the corrosive potential of any microscopic sand remnants still locked inside the inaccessible internal bays. They deliberately preserved the heavy sand scoring along the fuselage spine. They intentionally retained the dull, abrasive wear patterns etched into the metal by the shifting desert trench. The surviving remnants of the crude adhesive tape and protective netting used to seal the aircraft were strictly documented and preserved as vital contextual evidence. The overarching goal was stabilization without sanitization. Today, the heavy airframe rests on its original undercarriage in the public gallery. It is presented in its raw, fragmented state, a heavy aerospace structure carrying the permanent scars of its subterranean concealment. The artifact remains locked in its final condition, an unyielding record of survival by burial.